Hello, science students. Welcome to today's lesson about electromagnetic waves. To understand an electromagnetic wave, it's important to recall what we've learned about mechanical waves. Remember that mechanical waves transfer energy. All waves transfer energy, but mechanical waves do it by vibrating, pushing, pulling, or generally colliding one atom or molecule with another one. As we look at our example of a transverse wave, you can see as those atoms and molecules move up and down as they vibrate and the wave moves from left to right. You can also see our longitudinal wave move left to right, but it has areas of compression and areas of expansion that move the particles parallel to its motion. Both of these waves, though, move by vibrating or moving, pushing and pulling on each individual atom or molecule within a material, which raises an interesting issue. Mechanical waves can't transfer energy through space. There's just not enough matter to transfer them through. So, the question is raised, how does the Earth get energy from places like the sun? A mechanical wave cannot transfer energy from the sun to Earth. While the Earth and the sun themselves are made up of matter, other celestial bodies like other planets, other stars, comets, asteroids are all made of matter, but there are these large expanses of area of nothingness where there is no matter to push around or pull around to transmit a mechanical wave. Instead, energy from the sun is transferred with electromagnetic waves. These electromagnetic waves are capable of transferring energy through empty space as well as through matter. And we call that energy that they transfer radiant energy. You'll notice that these two terms are added up on our key vocabulary section. It'd be a good idea to make sure that you record them in your notebook for later. Electromagnetic waves form when electrical charges move. If you think back to our last unit on forces and motion, we learned about some forces that act at a distance, and the electrical force was one of them. The electrical force showed you that different parts of an atom, like a proton or neutron, have charges, and they create electrical fields around them. When those electrical charges move, that electrical field moves as well. That changing electrical charge changes the electrical field. This change in electrical field makes a change in the magnetic field. And that changing electrical charge starts a wave of vibrating electric and magnetic fields that fluctuate or create what we call an electromagnetic wave. In this diagram, you can see that there is a charged particle, like an electron, that has an electric field around it. As that electric field moves up and down, you can see it depicted there in the red, where that electrical charge moves up, the electrical field moves up. When that electrical charge moves down, that electrical field moves down. And you also notice here in blue, you have the magnetic field. So as that electrical field changes and moves up, the magnetic field changes and moves to the left. As that electrical field moves down, the magnetic field moves back to the right. And so a changing electrical field creates a changing magnetic field. And these two are very, very closely tied together in so much that we call it an electromagnetic wave as opposed to just an electric wave or a magnetic wave. We combine the two because they are so closely related. You'll also find that electromagnetic waves have those same properties that we use to describe and compare mechanical waves. They have energy that they carry. You could say that one electromagnetic wave has more energy than another one. You could also compare them by their amplitudes, or their wavelengths, or their frequencies. Every electrical wave, just as every mechanical wave, also has a speed that it travels at. All of these properties help us define and describe electromagnetic waves. Electromagnetic waves, while we demonstrated earlier, are a combination of a changing electrical field and a changing magnetic field. We usually draw them with a much simpler diagram than you see with the red and blue magnetic and electric field components. Instead, we just draw it as a transverse wave because that disturbs those fields perpendicular to the direction of the wave travel, just like the transverse wave disturbs the particles perpendicular to the direction of wave travel. So in our descriptions of electromagnetic waves, you can describe them using terms like crests and troughs. The amplitude goes from the rest position up to the elevated crest or down to the depressed trough. And then you could measure a wavelength from the top of a wave to the next top of a wave, just like we learned about with transverse waves. Also, you'll find that mechanical waves and electromagnetic waves both change as they travel through different mediums. Electromagnetic waves tend to slow down as they travel through matter. And that's because they're just moving much faster in that empty space. And just like mechanical waves can slow down as they go from gases to liquids to solids, the same thing happens with those electromagnetic waves. They move faster and slower depending on the medium that they're traveling through. Electromagnetic waves interact with different media in the same way that mechanical waves do. Electromagnetic waves can be absorbed by a medium. And if you think back to our investigations with the laser pointers, there were some materials that laser pointer did not travel through. It was absorbed by. There were other materials that laser, or that electromagnetic wave, that light wave, was able to pass straight through, or it was transmitted, or transmission. They also could be reflected. They could be refracted, they could be diffracted, and they could be scattered. We saw all of these things as we were investigating these interactions of waves as we looked at both white light and laser light. Electromagnetic waves that reach the Earth generally come from the sun. It's our largest source of electromagnetic radiation. And that's simply because it's the closest source to us. If you look at all of the stars in the sky, each one of them is producing light, each one of them is giving off electromagnetic waves. But the sun is the closest one to us, and so it generally hits us with the largest amount. The very, 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 very hot and very, 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 very pressurized inside the sun create those different wavelengths of electromagnetic waves. The sun generally gives out ultraviolet waves, light waves, and infrared waves, which isn't really all that surprising. You may have seen sunscreens and things like that talk about the UV or ultraviolet rays that they block. An interesting thing is true though. All matter can produce and does produce electromagnetic waves, even yourself. That's because all matter contains charged particles that are constantly vibrating and moving. And as each one of those charged particles vibrates, it gives off electromagnetic waves. An interesting thing happens though when an object's temperature increases, the particles vibrate faster and produce higher frequency electromagnetic waves. We've learned that there are different types of electromagnetic waves, and your electromagnetic wave info sheet will help you identify all of the different types of EM waves that we have. But they all differ based on their wavelengths and their frequencies. Longer wavelengths tend to have smaller frequencies and carry less energy, while shorter wavelengths have higher frequencies and thus transfer more energy. As you take a look at this diagram of the electromagnetic spectrum, it includes those 7 different types of electromagnetic waves. You can see their frequencies shown with their wavelengths. You can also see an approximate scale of the size of some of those particular waves. For instance, radio waves are on the scale of 10 to the second or 10 to the third power. 100 to 1,000 meters long, whereas gamma rays are 0.1201 times 10 to the negative 12, 0.0000000001, or about the size of a nucleus in an atom. That visible light that we can see falls in the range of the size of about one of those single-celled organisms you studied in 7th grade.